Hi, my name is Emmanuel. I'm from Cornell, and I'm presenting the DB-BERT system. The system relates to the good old saying, when all else fails, read the instructions. And that saying certainly applies to the problem of database parameter tuning, because database systems typically have hundreds of tuning parameters. You see some of them for Postgres on the left-hand side. And often our goal is to find good settings for those parameters in order to optimize the performance metrics such as latency or throughput for a specific workload and system. Now, in order to do that, of course, you could just start trying out parameter settings and observe the performance that you're getting. But it would probably be a good idea to, first of all, have a look into the database manual in order to read up on the semantics of parameters and on recommended values. And perhaps you also want to have a look at other text documents, such as blog entries about database performance tuning or discussions on forums such as DBA Stack Exchange. And all of this information will probably be helpful in order to find good parameter settings faster. In this talk, I'm going to transfer this piece of advice to the domain of automated database tuning. Currently, automated database tuning tools often use reinforcement learning in order to select interesting parameter settings to try. Then they evaluate them in trial runs and select hopefully better settings in the following iterations. Now, the DB-BERT system that I'm presenting here also does that, but it doesn't start from scratch, but instead extracts useful information about database tuning from documents that it finds on the web. And until quite recently, this project would probably have been overly ambitious, but over the past couple of years, we had some amazing progress in the domain of natural language processing, which I'm exploiting here. And even if you're not working in natural language processing, you might have come across headlines such as the one that you find here, where advances in natural language processing have been discussed in the mainstream press. At the heart of those advances are two ideas primarily. First of all, there's the transformer, which is a new neural network architecture that allows to parallelize more easily compared to prior approaches and enables us to create very large language models with hundreds of billions of parameters. The other idea is a transfer learning, which means in particular that we can train on some natural language processing tasks where we have large amounts of training data, such as predicting obfuscated words in web text. And then we can at least partially transfer this knowledge to more specialized tasks, such as text to SQL translation, where it is much harder to obtain large amounts of training data. And the DB-BERT system exploits those advances. It uses the popular BERT transformer model, which has been pre-trained using large amounts of web text. It applies natural language processing in order to analyze documents like the ones that you see here. Those are documents about Postgres performance tuning. They are extracts from the Postgres manual, as well as blog entries about database performance tuning or discussions on forums such as Stack Overflow. And more specifically, our goal here is to extract the text snippets like the ones that you see here on the left-hand side, which recommend specific values for specific parameters. Those parameters and values are marked up in red here, except for the last hint on this slide, which recommends to use 6 parallel workers, but it does not explicitly mention the name of the parameter, which enables us to do that. In those cases, DB-BERT actually has to automatically infer which parameter we are talking about. And ultimately, we have to translate all of those text hints into arithmetic formulas that can be evaluated automatically. Now, here on the right-hand side, you see the associated arithmetic formulas. You see that some of them recommend absolute values, like the second and the third one, while the first one recommends a relative value, which depends on the amount of available main memory. Once we know that, we can resolve this recommendation into a concrete value. Now, the DB-BERT system takes as input a workload that we want to tune, as well as a performance metric we want to tune for, which could be throughput as well as latency. In addition to that, DB-BERT takes as input a set of user-defined keywords which describe the tuning scenario. And it uses those keywords in order to retrieve relevant documents via a Google search and automatically extract the corresponding text snippets. Of course, those tuning hints that we find on the web, they might be unreliable, or maybe they don't relate specifically to the workload or to the performance metric that we're interested in. So we have to validate them and perhaps adapt them. And in order to do that, DB-BERT executes a trial runs with the input workload in order to measure the performance when following specific hints that it extracts from text documents. After a configurable amount of tuning time, the output is the best parameter settings that DB-BERT has found so far. And internally, this tuning process is divided into two phases. We have the pre-processing phase, which happens once, and then we have the learning phase, which is iterative. In the following, I'm going to say a few more words about both of those phases. The goal in pre-processing is to analyze the input text in order to extract tuning hints, in order to translate them into arithmetic formulas, and in order to determine in which order we want to consider those hints in the following stages. So, for instance, we start with the user-defined keywords that you see here, which hint at the fact that we want to tune latency on the TPCH benchmark for the Postgres system. Now, DB-BERT extracts relevant documents via Google search, and from those documents, it extracts relevant text snippets that recommend settings for specific parameters. By analyzing those snippets further, we can find out which parameter they are referring to and what the recommended value is. And then finally, we decide an ordering in which those hints will be considered in the following stages. And this ordering takes into account the perceived importance of the target parameter, with the assumption that parameters which are frequently mentioned on the web tend to be more important for performance. It also makes sure that we don't consider too many hints about the same parameter before switching to the next parameter. Now, that is a high-level overview of the pre-processing phase. It provides the input for the learning phase. During the learning phase, our goal is to adapt hints, meaning we deviate slightly from the recommended values, to prioritize between conflicting recommendations about the same parameter, and to aggregate many different hints into few parameter settings, meaning few combinations of value settings that we evaluate via trial runs. In order to do all of that, I'm using a reinforcement learning framework, and that generally means that we have an agent which interacts with an environment. And the agent can influence this environment by actions, and it can extract information from the environment by making so-called observations. The ultimate goal of the agent is to maximize reward values that it receives from the environment, but at least initially, the agent doesn't know which action sequences reside in which reward values, so it has to somehow balance well between exploration and exploitation when selecting the next actions to execute. Now, specifically in the scenario here, the agent, that is the DB-BERT system, and the environment is characterized by workload and database system properties. The actions that are available to the agent relate to adapting values recommended in hints, prioritizing between conflicting hints, and deciding how to aggregate different hints into specific parameter settings. Observations are derived from the input text documents, and we have two types of reward values. First of all, there's rewards for configuring the database management system successfully, so trying out parameter values that are actually accepted by the database system. The second reward component is proportional to the performance improvements that DB-BERT achieves. So if the tuning metric is, for instance, throughput, then the reward values will be higher if a specific parameter setting maximizes throughput during a trial run. So that's a very high-level overview. Now, to make things a little bit more concrete, I'm going to show you a little demo of DB-BERT in the following. In order to use DB-BERT, I first of all select the collection of text documents to extract hints from. Here I'm selecting a collection of text documents that has been generated automatically via a Google search and based on the keywords Postgres performance tuning. Then I select the hardware properties of the system to tune for, the database to tune on, and finally the performance metric as well as the workload to tune for before starting the tuning session. During preprocessing, DB-BERT identifies interesting text passages such as the one here, recommending to set the shared buffers parameter to 25% of available RAM. DB-BERT automatically extracts the parameter the text refers to, as well as the recommended value, and here it infers correctly that we are talking about a ratio of the total amount of available RAM. In the learning phase, DB-BERT can decide to deviate from those recommendations here, for instance, by multiplying the recommended value by a factor of 0.5. Also, DB-BERT assigns weights to each hint, which represent relative importance. In this case, the new settings for the shared buffers parameter are accepted by the database system, which already yields an assignment reward. Furthermore, after considering enough recommendations, DB-BERT will aggregate all of those hints into a combination of parameter settings to evaluate via trial runs. And here, as we get performance reward, it means that this parameter settings, they have improved performance compared to the default settings. And in the table above here, we see that the runtime has already decreased by about 1/4 on the example workload after just a few minutes of tuning time. In the experiments, I compared DB-BERT to other automated database tuning tools on different benchmarks like TBCH and TBCC, and for different database systems like Postgres and MySQL. Here, for instance, we see results for TBCH on MySQL. On the x-axis, we have a tuning time, and on the y-axis, we have execution time of TBCH for the best configuration found so far. And if you compare DB-BERT, which is the red line, for instance, against the DDPG++ baseline, it turns out that DB-BERT finds interesting configurations faster because it exploits information mined from text documents, which DDPG++ does not. When comparing DB-BERT against the keywords and supervised baselines, which are relatively simple approaches for extracting tuning hints from text documents that I have introduced in a recent publication, it turns out that DB-BERT performs better because it combines text mining with reinforcement learning, which enables it to deviate from recommended values and to integrate hints from different sources more flexibly. The results for TPCC, where on the y-axis now we have a throughput, are similar. And in the paper, you find many more experiments which vary, for instance, the system or the input text. You also find more information in the paper about technical details, such as how I'm actually modeling the reinforcement learning environment and how I'm aggregating possibly conflicting hints into common parameter settings. So in conclusion, I have presented the DB-BERT system, which mines information for a database performance tuning from text documents and uses them as a starting point for reinforcement learning-based exploration of the configuration space. Mining text documents is an advantage because it allows DB-BERT to identify important parameters quickly and to identify interesting value ranges for those parameters. And perhaps most importantly, this makes database tuning explainable because users can access the text snippets that have motivated DB-BERT to try out specific parameter settings and thereby gain some insights into why the proposed settings improve performance. Thank you very much for your attention. Now look forward to your questions.